We are SPO6 Red Time Mileage Tracker, and the three of us are going to be doing the final report presentation video. Justin Barker, me, Reese Gassner, and Jason Cho. Time Mileage Location is a Android mobile app we developed using the software development lifecycle approach. We wanted to enable users to track their travel distance and time of trips via GPS. We'll be talking about the SDLC process we use to develop the application. For requirements, we're going to be talking about our functional requirements. We're going to be doing an analysis on Flutter and why we used it and how we used it. Design, so our architecture and system design. We're going to have a lot of slides on development, which is going to be talking about how we implemented the features in our application, and then how we made sure those features work with testing. And after that, we're going to be having a demo. And then after that, we're going to talk about version control using Git, and then we're going to round that all off with our conclusion. The first step we took into the SDLC approach was finding our requirements. We found 4 requirement categories, being trip logging, organization, data storage, and user interface. After finding the categories, we found the functional requirements for each. Trip logging has 2 functional requirements. The first one is the user should have the ability to create manual entries by the user giving the total mileage and time of a past trip. The other functional requirement was the user can start a new trip that is being logged by GPS. The next requirement category was organization. The first functional requirement for organization was to allow the user to assign tags to any already logged trip. The next requirement was the user should be able to filter or sort trips by tags or any other entry-related properties, such as date, distance, and duration. The next category was data storage. First requirement was the trip data is stored locally into a CSV file on the user's device. The next requirement was the data should remain persistent after the user closes the application. And the last functional requirement was the application should read from the CSV file and rebuild the entry list once the user loads the application back up. The last category was user interface. The first functional requirement was a navigation menu that allows the user to access different sections and functionalities. The next requirement was the forms that the user would use to create a manual entry. And the last was the user should be able to view all entries, allowing the user to review, edit, and delete the entries. For the analysis step, we discussed Flutter and how the tools and technology is useful and relevant to the project. Flutter is a pretty important architectural component in developing our application. It provides a comprehensive set of tools, libraries, and features that enabled us to build a responsive and performant user interface. It allowed us to create a UI using a set of customizable widgets, which are the core building blocks of our application, encapsulating everything from the visual appearance to the way an application interacts with the user. Flutter also has very useful and important packages that we can use. For example, we used the geolocator package, which allowed us to implement GPS into our application. As you can see on the slide, that is the architecture of the Flutter framework. Flutter's architecture is designed for efficient UI handling, such as rendering, animation, and user input. It offers a smooth experience for cross-platform apps. User input is handled by widgets, triggering callbacks to the animation and build phases. The layout phase calculates each widget's size based on parent constraints, followed by the painting phase, drawing widgets based on the layout calculations. The composition and restoration stages optimize rendering, generating a layer tree which converts into pixels on the screen, ensuring high quality and fast rendering apps across the platforms. The next step in the SDLC process was the design. We split the design into 2 categories, architecture and system. We wanted to use a 3-tier architecture for our application. This is broken down into a presentation layer, application layer, and a data layer. You can see that on our slide. The presentation layer is the UI views and user input systems. It has the responsibility of user interface elements required for the application, like capturing and processing user interactions. The application layer is the driver. It is responsible for orchestrating core logic and operations of the application. And finally, we have the data layer, which serves as the foundation for managing trip data storage. The local data subsystem handles storage of trip records locally on the device. This was chosen over other methods of storage so that the application can provide fast and guaranteed access to data without an internet connection. The detailed system design of the app includes several key components focused on user interface views, trip tracking logic, and data storage. The UI View subsystem provides a clear visualization of the app structure, guiding the user from the home page through various functionalities such as settings, tracking methods, and history viewing. The dialog map that you can see on the slide is crucial for us developers and clients to understand the flow and state transitions within the app. The trip tracking logic component is packaged separately to handle the logging and calculation of trip details. Users can input start and end locations, dates, and distances within the app, automatically calculating trip duration. GPS functionality allows for real-time tracking, utilizing streams of geographical data to measure distance traveled, enhancing the accuracy of the logs. And finally, the data storage is managed through a system that ensures integrity, accessibility, and security of user data. This subsystem uses a combination of database and file systems to persistently store trip details, which can be accessed and managed directly from the app. The design prioritizes efficient data handling to accommodate the storage and processing of extensive travel data. You can see that we have the first slide related to development. To implement GPS into our application, we use the geolocator package within Flutter. This package provides a stream of position updates, which can be subscribed to for continuous tracking. All GPS logic is housed in a file called GPS trip. This file is able to work because of the GPS trip class we developed. This class starts with initializing instance variables that store your starting position, ending position, time, and total distance. The first method within this class is how the GPS trip logic starts. It sets the current start time and the current starting position. To get the current starting position, we have a method that can gather the first location with the highest accuracy using a method built-in geolocator called desired accuracy. With the trip started, it moves on to the method that is going to track the entire trip. It subscribes to the position stream that I mentioned earlier and listens for updates. When a new position is received, the distance between the starting position and the current position that the user is at right now is calculated using a method called distance between. Distance between is a method from geolocator that compares the latitude and longitude of two sets of coordinates. Once the distance has been calculated, the distance gets added up to the total distance variable, and the starting position is overwritten by the current position, and the current position is set to empty to wait for the next position from the position stream. Once the user ends the trip, the end trip method logs the end time and cancels the position stream and sets it to null. If the stream does not get set to null, then the stream of positions of the user's device will keep being sent. All the compiled data is then loaded into an entry table and formed into an entry for the user to see.
Our application will automatically tag an entry for both trip start and end provided there exists a matching location in the named locations list. By default, this is not enabled and the location list is empty. Users must indicate they want to add a new location to the list, wait for the device to get an accurate longitude and latitude values, and then label location. This location and label is then saved to the list for future use. We opt to store user data locally on the device's disk for privacy reasons. We looked into opt-in cloud storage, but ultimately decided our efforts were better allocated to implementing the remaining features. This local file simply follows a CSV formatting, delimiting each property of an entry with a comma. Choosing to keep the data local eliminates any reliance on internet connection. At the bottom of this slide are some example entries saved in the CSV file. This is implemented by loading our storage manager's buffer with a CSV formatted line and writing it to the file when the global list changes. When loading the list, each line is read from a previously generated file as its own entry. We made the list view centralized around a list builder widget. This widget takes the length of the list to be displayed and the value of each list entry, in our case the trip entries. The list view is the main interface the user interacts with. From here the user can start and stop GPS enabled entries, add manual entries, add new name locations to the name location list, and filter the global list. Users can also access the settings page from here. Users can set various parameters to apply a filter to the global list. The resulting list replaces the global list until the user opens the filter dialog and selects the reset button. Some parameters available to the user to filter by include the start, the end date, trip distance, and a list of space-delimited tags. The settings page allows users to manage various global states of the application. Unfortunately, some settings are placeholders intended for future development. What is implemented though allows the user to manage the name location list, toggle auto tagging, and flush the global list. Setting states are returned from the screen to the list view where they are referenced by the relevant app functionalities.
Alright, so for this section, we're going to talk about adding and editing entries. We're going to talk about adding entries first. To add an entry, a user will just press the button that has the plus icon. This will cause a dialog to pop up above the list view, which contains many buttons and fields, prompting the user for various properties of the new entry. The first two are date pickers to define the start and end time of the trip. Local date time objects start and end are updated on confirmation of the respective date picker. Following the date time pickers are two text fields, which prompts for the mileage and a list of tags, each separated by spaces. On confirmation of this dialog, prior to the generation of any new entry objects to add to the list manager, each field is verified by a sequence of checks to be legal and valid. If a trip is already being tracked by a GPS module, the user cannot manually enter a list. This is done intentionally because if a user is expecting to be operating a motor vehicle, they should not be attempting to manually enter trips. All right, that's the adding entry. We're going to move on to the editing entry section. For editing entry, an entry in the list can be tapped on by the user, which then causes the app to respond with a dialog widget, which is similar to the add entry dialog. But each user input is pre-populated with the selected entry's original values using the text editing controllers for the entry's tag list and mileage and dates via the date picker's start parameter.
Because we are a mobile app and we want to use location data, we are required by law and regulation to ask for it. Permissions are implemented in the Android manifest.xml file for Android and the info.plist file for iOS. In our project, getting permission is implemented in the method to determine position in our GPS file. It uses the check permission method from the geolocator package, which returns a location permission value. First, we test to see if even the location services are enabled on your device. If not, then it denies the use of GPS. If it is enabled, we check for permission. If permission was not already given, then we request it. If that is denied or denied forever, then the GPS is not initiated and it's handled accordingly. If enabled or already had permission, then the GPS can get your current position. Testing is the last step we use in the SDLC to develop our project. We generally applied integration testing as modules were implemented. So as each module sufficiently passed integration testing, we applied in-house acceptance testing. This is what you see in our testing plan. Our acceptance criteria for a test to pass is pretty simple. The first is that the module/feature passes if the associated requirement is well implemented, and then the next is that the implementation is generally bug-free in most use cases. And in the case that a bug is discovered, a new issue is raised on our GitHub describing the expected output, the real output, the estimated severity, and then the commit hash the bug was discovered in, and the steps to recreate it. And then now you see on the slide we have our test results. And so we have a few test results that, as you see, weren't mentioned in anywhere in the development or the requirements, such as the failing. So the add an annotation to a log trip, generate a report that summarizes every trip in a log, and report exports to CSV. These implementations were pretty bug heavy, and we got to the point where we just had a hard time getting them implemented. So when we were testing, we decided just to take them out completely, but we still wanted to show you that we tested them and that they just flat out didn't work.
This begins the app's demonstration. We're just going to open the app and show the state that it is when the user first opens the app. And we'll just start with a GPS-enabled location trip. So it's going to prompt us to grant the app permission to access device's location. And we'll just say while using the app for this case. And we'll give it a moment here to get a couple of GPS pulls from the app's, or from the device's GPS. I reckon that's enough time. So we can see duration 18 seconds, distance 0 because we didn't go anywhere. We'll add a manual entry here as well. We'll say I went somewhere on the 25th, and we'll 1959, you know what I mean. And we'll say it went from 7:59 to 10 or 8:59. And we'll say it was a 100-mile trip. It means we went about 100 miles per hour. And we'll give it a tag. We'll say example for this tag. And that trip is also immediately reflected in the entry list. So if we go through here, close the app, just want to demonstrate the app's persistence, that all the entries are reloaded from the disk when the app is closed and reopened. So I'd like to demonstrate the filtering now. So we can adjust the distance filter here, and that eliminates our GPS added trip because the distance of the GPS trip does not meet the requirements of the filter. We'll reset it there and just demonstrate the example. We'll say example, and then we'll also decrease that. So we don't get any trips because there's no trips that have example and the distance is within this range 0 to 75. But if we increase that back up to 75 or back up to 100, that example trip returns as expected. And we'll just reset the filter for the remainder of this demonstration. So now we're going to add a name location. And this kind of takes a moment, and unfortunately it doesn't actually notify the user that it's doing anything during this time other than the green location marker in the top right. But once it does come up, it'll show you the location, your coordinates of the current location, and then you can give it a name. So we'll just call this one, we'll name it example, just for simplicity's sake. Once we save that there, go to the settings, we can see that this was one of the later features, so it's got a little bit of bug to it. But we can see that location is on the list, and we can enable the auto tag locations setting as well. So once we do that, we can start a new GPS entry and we have to give it a little bit extra time now so that it can actually get the start and end location separately in order to properly label in order to properly apply tags. So I reckon this should be enough time. Yep, and as we see, the start location was the same as the end location, so it was tagged twice, and that is intentional because it allows the user to know what the start location was and the end location, though there might be some way or a better way to show the user that it is a start versus end, because that's kind of ambiguous at some points. Regardless, we can go into this entry and edit various properties of it. So let's say in that time I went 11 miles and I edit it, immediately reflected in the list. Or let's say I didn't go on that trip at all. I can delete it and it's gone, just like that. So another feature that's kind of vestigial from the testing phase is the flush list. So if we flush the list, it'll clearly delete all the entries in the entry list, and once we save it, they're all gone, leaving you with a blank slate to work from.
So for version control, we used Git, and then GitHub hosted our repository that allowed us for straightforward collaboration between group members. For each change or feature to be added, a new working branch would be created. Once officially implemented, the author and owner of the working branch would make a pull request on GitHub to allow other members to review and audit the changes. If the others were satisfied with the changes and no merge conflicts existed, the pull request would be accepted and merged into our main branch. And on top of main branches, we actually have saved all of our commits, so we can go back to each commit and see what changes are made if we need to. In conclusion, we are very happy with how our project turned out. We all put in a lot of effort into the design and implementation, and we're actually pretty glad on how it looks. We found agile methodologies to be really useful throughout our time with the project. It allowed us to construct our app in a burst of high effort. It's what allows us to really meet only twice a week, unless more work had to be done, and still get all of it done on time. We believe our app reaches the objectives we set out to create. It functions well, it's bug-free, and it has a very well-documented process. Our only regrets is that there were some features that were just not implemented into the final version. Those are the features that I talked about earlier in the testing slide. But we think this project led us to become more comfortable in our ability to cooperate in a group setting and problem solving with new technology stacks. Justin and I have never coded a mobile app before, but we all think we did a pretty good job in our first try and in our implementation. So thank you.